really excited to welcome Andrew Westbrook today. So he's coming to us as a postdoc working with Rashawn Cools and Michael Frank. So between the Donders Institute and Brown University. And he's been investigating how striatal dopamine signaling modulates cognitive control. And he's soon going to be moving on to start his own lab, which is very exciting. And before his current post as a postdoc, he was a PhD student working with Todd Braver at WashU in St. Louis, looking at neural correlates of subjective value during decision-making about cognitive effort. So without further ado, I'm really excited to welcome Andrew to tell us about what he's been working on in his postdoc.
Great. All right. Thank you, Lauren. Thank you for extending the invitation and also for organizing today's talk. I'm really excited about the opportunity to talk with this community and to meet with people over the next couple of days. So thank you for that. And it's true. I'm a postdoc now at Brown University and also with Rashawn Cools at Donders. But I'm going to be starting my lab at Rutgers University in 2023 in July next year. And so I wanted to flag if anyone's looking for a postdoc in working memory, decision-making, and neuromodulation and wants to work in the New York City, New Jersey area, feel free to reach out to me. But today I'll be talking about work I've done as a postdoc on the influence of striatal dopamine over cognitive effort and how we weigh costs and benefits. So I think cognitive effort is a very important and critically understudied question. I think there's a very important mystery about why our faculties for planning and decision-making and reasoning, or to flexibly bias our behavior in goal-directed ways, we treat as costly or punishing. Why is it aversive to stay on task, essentially? And why is it, what are the mechanisms by which we weigh the costs and benefits of staying on task? And then why is it that sometimes mental effort feels so much more aversive than other times? For example, if we have lots of rich opportunities in our environment, we find it particularly taxing or difficult to stay on task. Or we might be particularly or acutely sensitive to the pain of mental effort when we have to switch back and forth between tasks. And I think these are really interesting and illustrative contexts for learning about mental effort. And then another question that's very important is, why are there such big individual differences? So if you control for ability to perform these tasks, why are some people so much more willing to exert mental effort than others? And this has an important neuroscientific implications, but also psychiatric implications. So we can think about deficits in cognitive effort in disorders like schizophrenia or depression, and we need to understand what leads to deficits in cognitive motivation to understand why we have deficits in things like cognitive control and goal-directed behavior. So why should striatal dopamine influence cognitive effort? So for this, we turn to a canonical model of cortico-striatal action selection. And according to this model, in prefrontal cortex, we have a hierarchical representation of goals, from higher order, more abstract goals in interior prefrontal cortex that bias lower order, more concrete goal and action representations in posterior prefrontal cortex. So imagine that you're doing the Stroop task. You might have a representation of the goal to attend color rather than to read a word in more anterior regions. That's going to bias a lower level rule to bias our behavior towards pressing the button to respond to color stimuli as opposed to word stimuli. And according to this model, these goal representations are maintained in part through recurrent excitation. But they become instantiated or represented in the first place through cortico-striatal gating. And so the striatum has a big influence over what, the contents of working memory, what gets gated into working memory at what times to maximize reward. And striatal dopamine here plays a big role in shaping the strength of these cortico-striatal synapses, and therefore the policies that govern what kinds of information is gated into working memory over time. And so we extend this model one step further towards the higher levels of the hierarchy, where dopamine might not only influence, which dimension of the stimulus to attend to, but also whether or not we decide to exert cognitive control at all. So is it worth it to do well on the Stroop task? And how motivated are we to perform well when we're doing the Stroop task? So we think in this way, striatal dopamine can play a role in biasing our willingness to exert cognitive effort in that context. To test this hypothesis, I teamed up with Roshan at Anders and Michael at Brown, using a paradigm that I've used for several years now, looking at people's explicit willingness to do hard tasks for more money versus easier tasks for less money. And in this task, the harder task is the in-back, and so we can increase the in-back level to increase task difficulty, and we can offer more money to entice people to choose it versus a lower level, easier level of the in-back task for less money. And the basic prediction is that as the in-back level increases, it becomes harder and harder and should be therefore more costly. And so the subjective value of the offer to do the hard task should decrease. And this is exactly what we found in now dozens of studies and hundreds of participants. We find these nice monotonic discounting functions. So people give up more and more money to avoid the harder task, or conversely, the subjective value of that offer is decreased by these effort costs. We also see really big individual differences here. So we have some people with a high area under the curve. They're willing to do, say, the 6-back almost as much as they are to do the 2-back, and they have overall high levels of cognitive motivation. And we can contrast these people with folks like this who discount quite a lot. So even by the time they get to the 3-back, they've given up a lot of money to avoid the demands of that task versus the 1-back. And so these individual differences turn out to matter quite a lot. We can, if we look at AUC, we can predict the need for cognition, self-reported propensity to do demanding things in your daily life. We can predict goal success and achievement in academic domains and professional domains. We can predict differences in psychopathology. So people who have negative symptoms in schizophrenia or major depression tend to discount more overall than those who are than our healthy controls. And so even though this is a somewhat artificial task to ask people to trade off money for in-back tasks, it turns out to have important predictive validity. So to ask whether striatal dopamine plays a role in this decision, we used 3 tools. First of all, we looked at individual differences in the rate of dopamine synthesis. And so for this, we used 18-fluorodopa PET imaging to measure the rate of dopa conversion to dopamine in the presynaptic terminal. We also use drugs. So we use Ritalin or methylphenidate to block dopamine transporters. And by blocking dopamine reuptake, we increase dopamine in the synapse, and thereby we increase postsynaptic dopamine signaling. And finally, we use sulpiride, which is a D2 selective agent. Now, it is a dopamine antagonist. However, at the doses that we use, we think that we're targeting autoreceptors. And so even though it's a dopamine antagonist, by blocking autoreceptors, we think we should increase dopamine signaling postsynaptically, paradoxically increasing the postsynaptic effects of dopamine. And so with these tools, we think we can really triangulate in on the role of dopamine as opposed to something like noradrenaline, and also that we can focus on the role of dopamine in the striatum as opposed to other parts of the brain like the prefrontal cortex. So in our paradigm, we first have participants experience multiple levels of the in-back task, and we do this importantly before they get drugs so that everybody has the same basic experience learning about the costs of doing various levels of the in-back task before we manipulate dopamine levels with medication. And then we go into a discounting phase where we identify people's indifference points, how much money are they willing to trade off to avoid harder tasks. And then finally, we go into a choice performance phase where we can bias people towards choosing the hard task or the easy task, and we can control for choice difficulty based on the indifference points we identify in the discounting phase. Now, the little dots here on the screen also indicate that we're also looking at visual attention during the decision-making process, because it's long been known that visual attention plays a big role in choice paradigms like this one. So one of the first things that we found is, again, these nice monotonic discounting functions. So people give up more money to avoid harder tasks. But we also see big individual differences here in terms of the effect of dopamine synthesis capacity in the caudate nucleus. Specifically, those who produce dopamine at a higher rate or synthesize at a higher rate discount less overall, indicating greater willingness to exert cognitive effort. And so this starts to tell us part of the reason why we see big individual differences. It turns out that some people synthesize dopamine at a higher rate, and so all else being equal, they're going to be more willing to do harder things to pursue for reward than those who have a lower dopamine synthesis capacity. Next, we looked at the effects of drug, and we found a very important interaction between dopamine synthesis capacity and drugs. Namely, we find that on Ritalin and sulpiride, those who have low dopamine function will increase their willingness to exert cognitive effort for reward, while those who already have high levels of dopamine function show no effect of drugs. And this is important for a number of reasons. So first of all, it does help us have greater certainty that the effects we're seeing are dependent on dopamine as opposed to other neurotransmitters, and also that it's dopamine in the striatum that seems to modulate cognitive motivation. From a psychiatric perspective, the other important implication of this result is that if we look at a drug like Ritalin, which is widely used to enhance cognitive control and working memory function, those effects are often interpreted in terms of the impact of dopamine signaling in prefrontal circuits directly, or perhaps on working memory capacity. What we're showing here is that even when you control for working memory capacity, Ritalin seems to boost the willingness to exert cognitive effort. So perhaps motivation is part of the reason why Ritalin improves performance on cognitive control and working memory tasks. So why would dopamine increase cognitive motivation? So for this, we turn to another canonical model of action selection in cortico-striatal thalamic loops. And the observation that dopamine release can potentiate activity in a pathway of neurons that express D1 receptors. And so as a consequence of reward prediction error signaling over time, this pathway will become strengthened by the experience of rewards. And in economic terms, we can say the expected benefits of action are going to be represented in this pathway. In the indirect pathway where D2 receptors are expressed, dopamine signaling is going to lead to long-term depression and weakening of synapses. And so conversely, when we have lots of punishments, this pathway gets strengthened. And so over time, in economic terms, the pathway will come to reflect the relative costs of action. And so whether you take a certain cognitive action, like gating something into working memory, then is going to be based on, again, in economic terms, the balance of benefits to costs, which are going to be reflected in the strength of direct versus indirect pathway cortico-striatal synapses. So from this very simple model, we can make predictions about behavior, specifically as a function of dopamine, what is the probability of making the high effort choice in this task? And so we can look at the probability of high effort choice as a function of the difference in subjective value between the hard task and the easy task. And the straightforward prediction is that as the high effort task becomes more valuable, you should be more likely to choose it overall. Now, the effect of dopamine signaling has a very particular effect on the shape of this psychometric choice function, namely, because dopamine release and dopamine binding at D1 receptors will potentiate that pathway, you should become more sensitive to benefits and less sensitive to costs. So what's the effect on the choice function? Well, on the right-hand side of this curve, the hard task is becoming relatively more beneficial. So we should see that that side of the curve becomes steeper when dopamine levels are higher. Whereas on the left-hand side of the curve, the hard task is becoming more and more costly. And so that curve, because you're less sensitive to cost, should actually flatten out when dopamine levels are higher. And so the prediction is basically that when dopamine levels are higher, we become more sensitive to benefits and less sensitive to costs. And we get a very particular kind of choice function, which is steeper on the right-hand side of this curve and shallower on the left. And that's indeed what we see. So if we look at individual differences in dopamine synthesis capacity, those who synthesize dopamine at a higher rate have steeper functions on the right and shallower functions on the left. But we also see this with respect to drugs. So both of the drugs that we think should boost postsynaptic dopamine signaling, methylphenidate and sulfuride, tend to make the curve steeper on the right and shallower on the left. This suggests that dopamine influences our sensitivity to benefits versus cost information, but we wanted to control for the possibility that drugs would somehow bias people to pay more attention to benefits information versus cost information, or the degree to which we attend to the hard task versus the easy task. And so for that, as I mentioned, we used eye gaze to look at visual attention. And one of the big predictions from lots and lots of studies showing that visual attention influences or biases choice behavior is that if we look at an option more, we're going to be more likely to choose it, controlling for the differences in subjective value. And so I can tell you right away that we did not find that dopamine influenced how much people look at benefits information or cost information, or how much they look at the hard task versus the easy task. But we did find the classic result, which is if you spend more of your time looking at the benefits of an action or the cost of an action, you're going to be more likely to choose it. So in this case, if you spend more time looking at the hard task cost or the hard task benefits, you're going to be more likely to choose that option, all else being equal. We also see a very sensible interaction here. So the effect of this curve the curve rather is steeper. If you spend more time paying attention to benefits, you're going to be even more motivated to choose the hard task than you will if you spend more time looking at hard task costs. So it's a very sensible effect of attention to benefits versus cost on choice, along with the predicted effect of overall attention to one choice alternative versus another on the final choice. So we wanted to capture these dynamic effects, and one of the things that we did is to adapt the classic attention drift diffusion model. And so according to this model, we might accumulate evidence over time towards choosing the hard task or towards choosing the easy task. And if we, let's say, spend more time at the beginning of the trial looking at the benefits of the option, then in this toy example, we're going to accumulate evidence at a high rate towards choosing the hard task because it's more beneficial. Then if we shift our attention to the costs, we might decide that the easy task looks more attractive, and that will either flatten out our drift rate, or it might even, we might accumulate evidence in the opposite direction towards choosing the easy task. And again, in this toy example, we attend to benefits and ultimately we choose the hard task. Now, one of the things we observed is that there's a very clear effect of what we call a kind of gaze bifurcation. And so by this, we mean that about 750 milliseconds before people respond, before they actually press the button, people start to allocate their gaze towards the option that they are about to choose. And I think there's some interesting ideas about why this might be happening, but for today's talk, the question is really, during this early phase, this pre-bifurcation window, when people are looking back at between benefits and cost information, does dopamine modulate the effect of attention to benefits versus costs on choice? And in short, we find two bits of evidence that it does. First of all, we find that if you have higher dopamine synthesis capacity, the interaction between the difference in benefits between the options and attention to benefits is amplified. We also find that it's higher, or amplified rather, on methylphenidate versus placebo, suggesting that attention does matter, but also that the information that you're attending to, especially if it's benefits information, can be amplified when dopamine signaling is higher. So a few key take-home points. First of all, I showed you that striatal dopamine can increase the explicit willingness to exert cognitive effort or to do a harder working memory task. I also showed that dopamine increases effort specifically because it makes people more sensitive to the benefits versus the costs of cognitive effort. And finally, that dopamine can amplify the impact of attention to benefits on choice. Now, in this explicit paradigm, you might be wondering, it's one thing to show that people are prospectively more willing to exert cognitive effort when dopamine signaling is higher. But what does dopamine do during performance of the task? Does it actually increase our reliance on working memory? And so for this, we use the same set of participants, and later, after we administer drugs, we had them perform the reinforcement learning working memory task developed by Ann Collins and colleagues. So in this task is specifically designed to to separate out the contributions of working memory and reinforcement learning to performance. And the way this happens is that in one block of trials, you have to learn the mapping between a set of stimuli and one of 3 button presses. And it proceeds by showing a stimulus, and then people make one of 3 button presses to respond, and then you deterministically get a reward if you're correct or a punishment if you're not. And you can imagine that when you're performing this task, you can use a straightforward reinforcement learning process, so you can accumulate rewards and punishments over trials, and then use that information to select the correct action. Reinforcement learning is a kind of slow, incremental process, but ultimately, you're going to cache the correct values associated with the correct stimulus response mappings, and you'll be able to respond accurately. Intuitively, another way to solve this task is just to use working memory. So we can just remember what we did 1 or 2 trials ago and use that information to bias our behavior appropriately. Now, to determine how much working memory contributes in learning, one of the things we can do is we can manipulate set size. So in one block, we might only have 3 items to learn about, but in another block, we might have 5 items to learn about. Now, we would suspect that working memory will contribute less when we have 5 items to learn about, because working memory famously is capacity limited. So we might start to exceed our working memory capacity. Working memory is subject to delay effects. And so rather because of interference or because of just decay of the working memory trace, if it's been more and more trials since we've last seen a stimulus, then working memory can play less of a role because of decay. And so by comparing performance in smaller set size blocks to larger set size blocks, we can tease apart how much working memory is contributing to performance of this task. And in so doing, in this paradigm, this larger paradigm, we can ask questions about how much whether dopamine influences the propensity to rely on working memory. Importantly, I'd like to also bookmark that there have been lots of studies which have suggested that dopamine plays a role in reinforcement learning mechanisms. But very rarely do you see that people control for the contributions of working to performance on stimulus response learning tasks. And we can imagine that this is going to have a big influence over how we interpret, say, a reinforcement learning rate. So if you're doing a task in which there are fewer items to learn about, working memory may play a bigger role, and you're going to have what looks like a very high effective learning rate, because working memory is very fast. You can instantly remember what you did on the last trial. And so I think it's important to ask whether striatal dopamine can influence the reinforcement learning process and machinery when we properly control for these contributions of working memory. And one of the first things that we saw in this in performance of this task is, as predicted, that accuracy increases with set size. So in all blocks, people asymptotically perform quite well, but accuracy jumps up faster for smaller set sizes. Now, again, if you were to fit a classic Q learning model to this task, it would do a very bad job of capturing behavior. It would not capture individual differences in set size. You could do something sort of arbitrary, like allow the set size to vary allow the learning rate to vary by set size. But this would be a complicated model, and it would also be hard to understand by what mechanisms the learning rate should adapt to set size. A better explanation, we think, is that working memory contributes to a greater degree in small versus large set size blocks. So in particular, in a block where there's only 2 items to learn about, we can just remember what we did 1 or 2 trials ago. And so accuracy is going to jump up much faster than it will if we have, say, 5 items to learn about. Now, importantly, we also find that striatal dopamine plays a role. The distinction between the dotted and the dashed lines here is that of, again, dopamine synthesis capacity in the dorsal caudate nucleus. And we find that those who synthesize dopamine at a higher rate show higher accuracy on smaller set size blocks, and particularly they do so early in a block versus late in a block. So on the x-axis here, we have plotted the iteration number of a given stimulus, and we find that late in a block, everyone asymptotes at a high level of performance, whereas early on, there's a big differentiation by set size and also by individual differences in dopamine synthesis capacity. Now, this distinction between early versus late is important because, as Anne has also shown in earlier work, it appears that we rely to a greater degree on working memory early in a block versus late in a block. And this makes sense because the reinforcement learning machinery is reliable. It has practically unlimited capacity, and we can rely on these cached reinforcement learning values, but it's a slow process, so it takes some time to catch up. So while RL is catching up, working memory can fast and flexibly contribute to performance on this task. But then over time, late in a block, we'll settle on those relying more on reinforcement learning to perform the task. So this first bit of evidence suggests that that we rely, so I have other data here to show that early in a block, we rely more on working memory, and later in a block, we rely more on reinforcement learning. The first piece of evidence is if we look at the effect of set size on accuracy, and we can see that early in a block, set size has a big effect of decreasing accuracy with higher set size. But we can also see again that those who have higher dopamine synthesis capacity show overall better performance across all set sizes. Late in a block, by contrast, we see no effect of set size. It's basically flat. So I think it's pretty clear qualitative evidence that, that we might rely on something like working memory, which is sensitive to set size early in a block, whereas we rely on our cached reinforcement learning values late in a block. We also see that the effect of dopamine synthesis capacity tends to be attenuated late in a block. It's much more robust early in a block. So this suggests that perhaps those who have higher dopamine synthesis capacity rely more on working memory, and that boosts their performance early in a block. Whereas late in a block, when we rely more on reinforcement learning, individual differences in dopamine synthesis capacity may matter less. We can also see evidence of this distinction between early versus late reliance on working memory if we look at the effect of delay. So I mentioned earlier that, famously working memory is subject to delay effects. And we see very clearly on placebo that early in a block, we have very strong delay effects, whereas late in a block, there's no delay effect. We also see yet again here that those who have higher dopamine synthesis capacity tend to perform better than those who have lower dopamine synthesis capacity early in a block when we think that we're relying on working memory to a greater extent. We can compare across drugs and look at performance, and we see that overall methylphenidate tends to show higher accuracy on this task, and sulpiride tends to show lower accuracy on this task. To illustrate this point, we can look at asymptotic performance or late in a block, and we see that asymptotic accuracy is higher on methylphenidate than it is on placebo, and it's lower overall on sulpiride. And so it looks like whereas individual differences in dopamine synthesis capacity predict individual differences in performance early in a block, late in a block, it looks like methylphenidate seems to have a bigger effect. And so perhaps methylphenidate is, this is evidence that methylphenidate is boosting the reinforcement learning machinery, and it maybe does so controlling for working memory. Further evidence that methylphenidate might impact on reinforcement learning is if we look at the effect of previous correct iterations on the accuracy rate. So imagine that you're going through the task and you get a reward. According to the classic story, we should have a positive reward prediction error. And if that's dopaminergically mediated, that should lead to greater accuracy on the next trial that will, to a greater extent when dopamine levels are higher. And that's indeed what we see here. So if we contrast the curve for methylphenidate versus placebo, this learning curve is steeper on methylphenidate versus placebo, suggesting that when we increase dopamine in the synapse, that we can speed reinforcement learning, again, controlling for working memory. So to take stock, the behavior so far implies that both working memory and reinforcement learning contribute to SR learning. And again, I want to bookmark that it's important to control for both of these contributions if you want to ask questions about how much dopamine modulates one versus the other. Also, we have evidence that working memory contributes, but it does so more early on in a block when we're just becoming familiar with the stimulus set. It does so more at smaller set sizes and also at shorter delays. But then later on, when RL has the chance to catch up, it seems to contribute more, and it does so also at larger set sizes and at longer delays where we'd really be taxing the limits of working memory. I've shown you that those with higher dopamine synthesis capacity tend to perform better earlier on in a block, and this suggests that dopamine synthesis capacity predicts greater reliance on working memory. There's also some evidence so far that methylphenidate seems to, in contrast, boost the reinforcement learning processes controlling for contributions of working memory. So the behavior implies this, but we'd like to have a little more certainty. And so one of the things that we did was to fit an adaptation of Anne's original reinforcement learning working memory model. And in this adaptation, we have parallel RL and working memory modules. So the RL module, or the RL system rather, is a standard Q-learning module that has a single parameter, in this case, a learning rate parameter. And in parallel, we also have a working memory system that works as you might expect. So first of all, you get one-shot learning. So if you have a reward on the next trial, the Q value goes all the way up to 1. Whereas if you get a punishment, it goes down. Now, we've noticed that, as many others have, that people tend to pay more attention to when they're right than when they're wrong. So this gamma term here accounts for what we refer to as no-go neglect, or the neglect of punishments. We also see that, according to our model, we also have a working memory forgetting term. So epsilon here determines the rate at which unobserved stimulus response pairings are going to decay back to baseline, which is exclusive to the working memory system and not the reinforcement learning system. So we now want to combine these Q values together. So the first thing we do is we convert Q values into probabilities of actions. And then we determine an action based on a linearly weighted combination of what our reinforcement learning system is telling us versus what our working memory system is telling us. And we do so in proportion to this term omega. And omega is essentially a term which defines our overall reliance on working memory. And that term is sensitive to this parameter rho, multiplied by the ratio of working memory capacity to set size. So intuitively, we're going to rely on working memory less when we have larger set sizes, and especially when it starts to exceed our working memory capacity. It's also proportional to the ratio of a working memory capacity to delay. So again, if it's been more and more trials since we've last seen a stimulus, working memory can contribute relatively less. So the key parameter in this case is this rho parameter, which defines our baseline propensity to rely on working memory, controlling for all of these other factors. And the first thing I want to show is that this model does a great job of capturing, say, set size effects and the effects of iterations, of prior iterations on performance. It does a good job of capturing the individual differences in dopamine synthesis capacity, but also the effects of early versus late performance on this task. And it also captures early versus late performance as a function of the delay since the last time you've seen a stimulus. So overall, we think this is a very good model of behavior. And we can start to interpret the individual differences in the parameters that we estimate. And we find that, as predicted, dopamine can boost both reinforcement learning and working memory. Specifically, we find that on methylphenidate versus placebo, there's an increase in the effective learning rate alpha in the RL system. And this is mediated by an increase in learning rates, specifically for those who have high dopamine synthesis capacity. And so if you synthesize dopamine at a high rate and you take Ritalin, we'll see that your reinforcement learning rate will increase, controlling for the degree to which you rely on working memory. And then if we look at this term rho, which describes our propensity to rely on working memory, we find that on placebo and on sulpiride, those who synthesize dopamine at a higher rate will rely on working memory to a greater extent. And so this supports the story that we saw from behavior, where Ritalin seems to increase the RL learning rate, controlling for working memory, and at the same time, individual differences in dopamine function predict greater reliance on working memory. So key take-home points: dopamine caudate nucleus dopamine synthesis capacity can boost performance early in learning, suggesting that it increases the degree to which working memory contributes. That methylphenidate can boost accuracy asymptotically, and it's consistent with the hypothesis that pharmacological increase in synaptic dopamine can increase our rate of reinforcement learning, controlling for working memory contributions. We also found, although I spent less time on it, we also found that sulpiride reduces accuracy overall, and we believe there's a bit of a mixed story here where sulpiride is undermining both the RL and the working memory machinery, leading to reduced accuracy. Now, going back to the original story, can dopamine influence are the way in which we learn about the cost and benefits of actions, in this case, cognitive actions, working memory actions. And so what we did to assess this question is to give people, we randomly selected stimuli from the learning phase. We give people pairs of options, and we said, we instructed them to pick the option which was rewarded at a higher rate during the learning task. Now, they weren't supposed to pay attention to reward statistics, that would be an incidental effect. But it turns out that people can faithfully pick, they can pick which was rewarded at a lower rate and which was rewarded at a higher rate when we give them this probe at the end of the learning phase. And so what that looks like is that the probability of choosing the more rewarded option increases as the difference in reward statistics increases. So overall, people choose the more rewarded option at higher than chance, but the degree to which they do increases as you go, as there is a larger and larger difference in actual reward statistics experienced during the task. So people do track incidental rewards. What I'm also showing you here is that there's an interaction between the difference in actual reward statistics and the mean set size of the block from which the stimulus was taken. Why would there be this interaction? So Anne has shown in prior work that if you rely more on working memory, even though it speeds up the effective learning process, there's a paradoxical influence on reinforcement learning. Namely, if you're holding in mind the correct stimulus response pairing, then you're going to reduce your reward prediction error, and the RL process will be paradoxically slowed. And in this case, what we're seeing is that after the learning process has taken place, those items which were learned in a low set size block where we're relying more on working memory show effectively weaker cached RL values. So we're less able to differentiate the distinction between the reward statistics in this case than we are in a high set size block where you have to rely on reinforcement learning and you build in more robust cached values. But the key question is, does dopamine influence sensitivity to effort costs? And what this graph is showing you is that if we control for differences in actual reward statistics between the options, people are less likely to indicate that an object or an item that comes from a larger set size block was rewarded more. And so on the x-axis here, we have the difference in set size between the option that actually received higher rewards and the one that received fewer rewards. And we can see very clearly in both placebo and methylphenidate that people are less likely to choose the option that came from a larger set size block. And the way we've interpreted this effect is that it's like an effort cost thing. Essentially, if you're getting rewards and punishments, and let's say you receive a reward in the context of a high effort block, when there's high working memory demands, we discount that reward. And so as a result, the reward we learn is effectively less rewarding. It predicts perhaps fewer benefits and are higher costs. And importantly, we show that there's an interaction here with drugs. So this curve is shallower on methylphenidate versus placebo, suggesting that methylphenidate is attenuating the effect of effort cost learning on incidental learning about rewards and punishment statistics. So we'll add to our list of key take-home points here that effort costs discount reward values, and these effort cost effects are blunted by methylphenidate versus placebo. So I'd like to end by thanking the folks who've worked on this project with me. I want to thank my mentors, Roshan and Michael, for their incredible mentorship and the opportunity to work with this data, and also the team at Donders who helped collect and analyze this data. Thanks also to the NVO and the National Institutes of Mental Health for funding this work. And I'd also be more than happy to take questions. Thank you.